And if anybody wants to talk to me about those, let me know. I'm not opposed to having a discussion. Okay, so you guys got homework coming now that we're through the first exam. So I want to do one of the problems. We're going to do number 12, but it's related to number 11. Okay, 11 has no friction. If you can do 12, you should be able to do 11. Okay, so we're going to do 12. Now, that's 13, 14, and 15 on below is going to be for you for homework. We'll talk about it. But generally it's this, guys. No problem ever in your life from this day forward will come without friction. Okay? There's always something involved. Whether it's brand new cast iron pipe, or if it's concrete line pipe, or if it's glass pipe, something's going to have friction. So we're going to need to look that up. So we're going to have to go back to the book for some tables, and we'll flip open there, and I'll put the screen up. I was going to copy them out this morning, and I forgot to. So, all right. So literally what we got here is a reservoir with an 8-inch diameter pipe, 50 feet long, that discharges freely. The water surface elevation of the reservoir is 410 feet. The elevation in the center of the pipe at discharge is 375. Neglecting friction, determine the velocity in the discharge Q, the end of the pipe. Now, with 12, we're going to do the same thing, but we're going to add the friction in. So, picture is worth 1,000 words. Okay, we're going to be at 410, 0. EL. Okay. Now, I'm going to draw this really simply. You don't have to draw this part, but I want you to understand something, okay? It's 8-inch diameter pipe. Do I care if it's 8 inches that goes like this? So that the center line here is at the elevation? Nah, don't give a damn. Okay. So, literally, I wanted you to pay attention to that because most of the time what happens is they draw the stupid thing so that it's like this. Okay? And then mark the center line elevation as 375 or 372.5. Okay? And it's important to know that so that you're not always looking for a straight pipe, because we like them run straight, but not always do they do that. Okay, so things get in the way. All right, let's see what else we got going on here. It's 50 feet, so let's do this first. We got 8-inch diameter, and it's new cast iron. Okay, and we have 50 feet. Now I should check this to make sure something's not stupid here. It doesn't say in the problem, but I'm going to assume that it's 50 feet down the incline. They could give it to you with a run over rise, or they could give it to you as 50 feet horizontally. In this case, this is a safe assumption. I'm just checking the answers here to make sure that they weren't using that any place to be horrible, but the answer is no. Okay. All right. Now, how do we start this? Anybody remember? It's only been a week, so don't feel like you've... What's Bernoulli's equation? Whoa, really tough. Remember pressure. Okay, let's start this way. Pressure 1 over specific weight plus velocity squared 1 over 2g. So far with me? Plus z1 equal to p2 over specific weight plus velocity squared second velocity over 2g plus z2 plus, now we're going to have the HL, the head loss. Okay? First equation, right? What's the next one we got to play with? We're going to get there, yeah. Sorry, I should be a little more specific. So, to answer Brendan's question, let's do this. What are we going to eliminate first? What goes on at point 1? And I guess we should label this point 1. And point 2 down here at discharge. What goes on at point 1? What are the things that help you make Bernoulli simple?
V1 squared over 2g, 0, right?
There's no velocity because there is considered to be infinitely large. Okay? And you could almost go to the same thing as a constant head, so it fills in. Okay? What about P1? P1 is open atmosphere. Cool. Does that make life easy? Yes? Okay. About P2? Okay. And that leaves us our Z's, which don't cancel out. Our velocity 2, which is what we're trying to find anyways, right? And then the only other mix to this puzzle is HL. Okay. So now, I'll go back and refresh your memory on HL. So HL is the friction times the L over D V squared over 2G. Remember that mess? And in this particular case, it's going to be V2. Cobwebs getting dusted off a little bit? Let's see. We had Monday. Wednesday was asphalt day. Thursday was nothing. Friday was probably nothing. Saturday you probably slept in again. And then Sunday you wonder what I have to come back to school on Monday. No. Actually, you took an extra day. So good? Okay. So we can find the velocity, right? That's easy. We're going to rewrite Bernoulli's here, except we're going to need to have this information in here. Okay? All right. So a couple things along the way here. We know we got an 8-inch diameter pipe. Okay. And believe it or not, with the right tables, you can look these up and get the actual inside diameter. But what you're going to be looking for is in terms of feet, right? So assuming that we're just going to play with 8 inches, divide that by 12, and that's equal to how many feet? Calculator time, unless you want to do the math and reduce it. 2/3. So 2/3 is what in terms of decimal? 0.67. Close enough. Okay. So 0.67 feet. That'll make our lives a little easier and don't have to do any conversions later on. Word of wisdom. And it took me many years to figure this out. But in my little notebook I keep my jobs in when I do things. I have take a few minutes and just write yourself down all the inch to feet conversions. Because it'll save you a lot of time down the road. Okay? And really, they're just simple. 0 over 12, 0. 1 over 12, 1/12, and whatever decimal equivalent is. Okay. Because most things you're going to need is going to need to be in decimals. Right? You don't really multiply fractions very well. It's a woodworking skill, but not a engineering calculation skill. And nobody cares about 30/2 of an inch. But we do care about 1/4 of an inch, which is 0.25, right? It's nice to have all those down there. Some are easy to remember. Okay? Some of them aren't so easy. 1/12 is 0.083. Just use it all the time. Okay? So far, so good. Okay, so let's start solving this thing. Let's stop wasting time today. All right. So we're looking for now I'll tell you what, let's work it out this way. So Z1, what's Z1? That's 410, right? So 410 feet is equal to velocity 2 squared over 2g plus Z2 is 372.5 feet plus the friction, the L, D, V2 squared over 2g. Okay. Fortunately, you're just going to wind up with a couple extra V's in there, but we can manage this trick. Okay. And now if we bring all the V's to the left side, we're going to get out of there. Oh, wait a minute. I can do this too. We can do L. We know is 50 feet. And we know it's 0.67 feet there. Okay. All right. So 410 is equal to V squared over 2G. And it's going to be, no, did I do that right? I'm not doing that right. Guys, do the math with me here. Somebody, I'm going to screw this up. All right, so let's get so it's 410 minus 372.5 feet. Okay, then we're going to, this is negative, that's negative, minus the friction times 50 feet over 0.67 feet. I did that wrong. I am looking for V2 squared over 2G 1 plus 50 over 0.67 F. No. We got to get to that answer with some reductions in there. All right, let's check things here. So I want 410 minus 372 is 37.5 feet. Minus F, which we got to go find, times 50 over 0.67 is what number?
17.
74 point. Actually, you don't need any units on it because they cancel out. And we are not getting to this setup here. 1 plus, 1 minus, 1 plus, 1 plus. Did something stupid back in here where I didn't take the velocities out. That goes to that side. Oh, duh. Sorry. Logan, you're going to hate me today.
That's all right. I got white out.
I got white out. Let's do 410 minus 372.5 feet. That's V2 over 2G. And then I got V2 over 2G. And then I can wind up with 1, as I'll take out the V2 over 2G and multiply it times 1 plus that. Cool. And that leaves me 37.5 feet. And if we take V2 over 2G equal to I'm making a hell of a mess of the math here. What have I done wrong? We're going to divide this by 1 plus friction. And actually, I'm going to multiply that times 74.63 F. Yes? No? It is right? Cool, it just looks wrong. Maybe it's Monday, and I'm just making this more complicated than necessary. All right, so we got V is equal to the square root of 375 feet over 1 plus 74.63 times friction, which we got to go find. And then we're multiplying that times 2G. So that'll be the equation we're going to solve for, but that's not the beginning or the end. Well, that's actually the beginning. Definitely not the end. All right, where was it in this book? Right here. Okay, Dr. Regal and our clipboards and sticks. Let's swap over on the screen here for a minute so you can see this. So we got to go to page 62, table 1.4, and we're looking for cast iron new. Okay. Remember I said we had to figure out what the epsilon was to use the Moody diagram. Hanging with me so far? Okay. So we want 0.00085. 3 zeros, 85. Okay. So we're going to need that value. So epsilon, and I'll bring up this screen back here in a minute. Okay. Okay. Then we're going to take it from there, and we're going to go over to Moody's here. All right, we're going to go find that friction value. Okay. Cool thing is I gave you this handout, and I'm going to pull it forward from last week's lecture and put the diagram in here, and we're going to do it. Okay. But unfortunately, you need this table. Okay. So this is from table 4-1. Page 62. Okay. Me personally, it wouldn't hurt my feelings if you took that table and rewrote it someplace where you could find it quicker. Okay, like you're going to put it on a cheat sheet. Now, I will warn you of one little thing. Okay? This table looks really great from the standpoint of its new cast iron. How long is cast iron new? Till the day I run water through it. Okay? And what you really need to pay attention to is you're designing for a brand new condition. It happens once in its lifetime. Okay? It's like a brand new baby. It's only new 1 second. And after that, it's a human being that's on the planet. Okay? Same thing with cast iron plate. Same thing with all this plate. Okay? So these are really nice numbers, but you're probably going to find out when you're really doing design work, you want to correct that number so that it's used to having some rust on the inside. The surface roughness is rougher. Okay? So we'll probably crank it up to something more like 0.001 something. Okay? Because it's going to be rougher. And you need to plan that because that's the condition that your pipe's going to be in most of the time. Okay? So I love these phrases, new, new, new. Seriously? Nothing's ever new. Okay? There are better tables out there. So when you get out in the field, we want to look for the right ones. Okay, so back to the chart here. And let's see if I can get the Moody diagram copied from the other day. Did I have it in here or didn't I have it in here? I didn't have it in here. Oh, that kind of stinks. Oh, cool. All right, hold on a minute. I'm going to pause the video here for a second. Okay. So we get our roughness off there, and what we're looking for is this side over here. So we're really looking for a relative roughness, and it's the D over epsilon. Okay? So here's a good point where we need to have that conversion done early. 0.67 feet over 0.00085. And we're going to get a number. Turns out to be whoa. 0.00127. Okay? Buddy following along? No? Oh, please tell me I didn't get the wrong. Oh, sorry. Whoa. Oh, hold on a minute here. Wait. Moody diagram is different in your book. Ah, bastards. Okay, sorry. Moody diagram in your textbook does epsilon over D, which is 0.00085 over 0.67, and that is 0.00127. And in this world, that's going to be a different number. Somebody give it to me. 784. Thank you. Oh, good catch. That sucks. Okay. Cool. Ah! All right, why do they do that? Just to be jerks. Just the ratio is all we're looking for, okay? Roughness over the diameter. This book I stole this from uses D over E. Your textbook uses epsilon over D. And we're going to need to pay attention to which tables we're using. So I may want to scan the other one. This is textbook. Expose Gribbon. And this one sorry for that. Okay. Either way, you can do this, and it's just a matter of knowing what the table chart you're working with is. All right. So we're working for 784. Where's 784 fall? Well, someplace between 750 and 1,000. Yeah. These are so precise. Okay? You're going to hate yourself. So the real trick is, as long as you get within the realm of possibilities, we're good. Okay? So 784. So let's put a little dash mark. Kind of about 775 would be halfway. I'm going to go right there. Fair enough? Yeah? Oh, yeah, sorry. Wow, it is Monday, isn't it? Kyle, I need some more yawning going on. All right, so up here. Actually, probably more, yeah, let's go close enough. It's not going to be precise, okay? Cool. Now we got that mark, and we're basically going to follow this curve over to wherever our Reynolds number hits. How do we find our Reynolds number? You guys thought this was going to be a boring Monday. All right, anybody remember Reynolds number? Your book uses an R. Some books use RE. But basically we're looking at what? Viscosity times what? No. Close. Yeah, it's the velocity times the diameter over viscosity. Okay? Cool, but we don't know something, do we? This is the part of civil engineering that drives me nuts, and it's going to drive you nuts. Okay? So a couple things. This is where we get into what's called numerical methods. So we know the velocity is equal to all this up here with F in it, right? Can we solve that? No, because we need the velocity. So how do we do it? Well, we start playing guessing games, okay? And you bounce around. You try to do 3 separate problems, okay? So let's try this on for size, okay? So if I took this up here, and let's clean this up a little bit because we want to do something with this 2G. So let's make this 375 over 1 plus 7463 F, okay, times 2 times 32.2 feet per second squared. And actually, let's do, let's leave it as v squared, okay, and make life just a little bit easier. What are we going to get? Anybody want to do the math? Anybody got a number? Okay. Let's do that. I'll do it. So we're going to wind up with V2 squared is equal to 2415 over 1 plus 7463, and we're going to assume a friction. Okay? And let me put a note right here. Okay? So that'll give us an answer that turns out to be 966. And then V2 is the square root of 966, which will be 31.1 feet per second. Okay? So that's first attempt. Now, why? How in bloody green earth did I even come close to making that guess? Wouldn't you like to know, Matt? Or don't you care at this point?
What are we assuming it as? Like, what's that number?
0.002. Okay. 0.02. Okay. So, I'm going to blow this up here in a minute. Everybody good over here? Yeah. So, it's not a guess. It's just random. I'm guessing because I got something to play with. Okay. So, if I look at 0.02, that's actually below where my surface roughness came in, right? Okay, so that's a pretty reasonable guess. But if I pick something like 0.015, I'm probably going to take you off to the side and actually ask you to do it again. Okay? Or if you pick something like 0.04. Make sense? Okay, so using that, we're able to then put in a V2 here that is the first assumption. Okay, so assume F to be 0.02 such that velocity 2 is 31.1 feet per second. And we plug that in, and we're going to get a Reynolds number of 31.1 feet per second times the diameter is 0.67 feet divided by, anybody remember this magic number? Okay. And that should come out with, what's the units on that? Feet squared per second. I think that's the right unit. Okay, because we want it unitless. And we're going to get 2.08 times 10 to the 6. Okay. Okay, so if that's the case, hold on. Everybody good and copied it down? Okay. That's the viscosity of water at, it's one of those, just memorize it, Matt. But yeah, don't feel bad. Just one of those cheat sheet items. Okay, 2 times 10 to the 8th, or 2.08 times 10 to the 6th. So we're really right here. Okay, so red line, let's have a ruler. All right, 2.08, and just going slightly to the right. Go up. Remember our red line is over here for that one. Okay, and if we follow that along, we go from there to where this would be right there. I will. So if we come across there, we're going to be right there. Okay? Make sense? So ideally, follow the curve. Okay, but you got to follow the curve between two curves. Okay, you okay here? So mark there, between this curve and that curve, we've got to draw an imaginary curve along this and follow that. Cool part, this side of the chart is pretty parallel to each other. It's not until we get over here that we start sweeping up. Well, we go here, and we go over, and we get this number. So what is it? According to the textbook solution, 0.21. Okay? Is that on the money? Actually, is that right answer or is that the next guess? I'm sorry. Yeah, it comes out as the friction for this one is 0.021 from the Moody diagram. Okay? Now, if you were good and you were on the nose, the answer should come out as 0.002, right? Because that's the assumption we made. Got Rory going okay. The rest of you? Okay. So I assume for our friction, 0.02. Okay. If my answer comes out as 0.02, we're good. Okay. Assumption was perfect. Hang with me? But because it's not, we should go do it again. And we refine our assumption. Okay? And see what happens. Now the cool bit is, this is actually probably the next best guess. Okay? So let's do it again with 0.021. Okay? I'm going to do this one in green this time. So assumption 2 with F as 0.021, that means our velocity changes this time. So V2 is equal to 2415 over 1 plus 74.36 times 0.021. And we're going to get a velocity 2 that's equal to 30.6 feet per second. Okay. Now we push that into Reynolds number. 30.6 feet per second times 0.67 feet divided by 1 times 10 to the negative fifth feet squared per second. And we get a new Reynolds number of 2.04 times 10 to the sixth. Okay. And we go to the Moody diagram and we get a friction factor of F equal to 0.021. We're good. Okay. So it took 2 guesses to get you there. All right. Now, the rest of the work, let me finish this off and we can call this done. And we'll play another one of these on Wednesday. So we know the velocity 2 is 30.6 feet per second. Q is equal to velocity 2 times the area. Our area of the pipe is pi d squared over 4 equal to pi 0.67 feet squared over 4, which is 0.349 feet. And then Q will be equal to 30.6 feet per second times 0.349 feet. And we're going to get 10.7. Whoops, that's now. This one's squared, and that one's squared. Feet cubed per second. And just to put you in terms of the old geeks that do this old job, CFS. Okay, CFF is cubic feet per second. Okay, it comes from those bozos that didn't have computers that used typewriters. Okay, so reviewed Bernoulli's, hit the friction equation, made you make some educated guesses, but we had to use some things to do it. Okay, and I'll set another one of these up for homework that you can practice today and see how it goes. Okay, and then a couple of the other ones shouldn't be too bad. No Justin today. Josh didn't show up, and neither did Logan. Okay. Cool. If you got questions on your exam, I'd be happy to sit down and talk to you about them. Otherwise, try to have a good day. And I'm